which are continuously produced by the decay of their thorium parents, which are usually contained on aquifer solids, and all of them belong to uranium and thorium natural decay chains. So the reasons why SGD is, radium are powerful tracers of submarine groundwater discharge is basically, first, because they are highly enriched in SGD relative to seawater. So this basically means that even if there are small inputs of groundwater to the coastal ocean, this will represent an important input, an important addition of radium isotopes to the coastal ocean. And this results in SGD often being the main source of radium isotopes to the coastal ocean. Also, radium isotopes, they have a conservative behavior in seawater. So this allows constraining, better constraining inputs and outputs. They have a wide range of half-life from 3 days of radium-224 to 1,600 years of radium-226. And these different half-lives allow combining different isotopes to estimate water ages, transit times, residence times, and also they can be used, different isotopes can be used to trace processes at different scales. Also, they belong to different decay chains. So sometimes you can identify different groundwater sources because they come from different lithologies that have different ratios between uranium and thorium isotopes. And finally, and also really important, they integrate all SGD inputs. So basically, it allows smoothing a little bit, this spatial and temporal variability that is typical of SGD, and it allows obtaining estimates for relatively large areas. So imagine that this is the coastal aquifer or saturated sediments. This would be aquifer solids or sediment grains, and this is flowing groundwater. So basically, radium would be continuously produced by the decay of the thorium parents, which are mainly located at the surface of the sediment grains. At the same time, radium will also decay, will also be removed from solution as a consequence of radioactive decay. And importantly, the production of radium will basically depend on the characteristics of the solids. So basically, on the content, on the concentration of uranium and thorium, and also on the specific surface area. All the radium that is produced by thorium can either be absorbed into the solids or dissolved into the water, and this exchange equilibrium, basically governed by for these absorption-desorption reactions, basically it's explained or it's controlled by the cationic exchange capacity and also by the composition of groundwater. When I'm saying composition of groundwater, basically pH, temperature, but mainly salinity. So if we have higher salinities, there will be a higher proportion of radium dissolved from the solids to groundwater. And finally, we have radium can also be added or removed from solution through weathering or precipitation processes, but these processes are usually less relevant than the other ones and are usually neglected. So this explanation can be translated in a simple one-dimensional equation where basically we evaluate the evolution of radium activities as a function of groundwater flow path, or in this case, as a function of time. So the evolution of these activities will depend on the production, but it will also depend on radioactive decay, as well as on the distribution coefficient, which is basically a parameter that weights the relationship between the amount of radium in the solids to the amount of radium in groundwaters, dissolving groundwater. So basically, it's a way of accounting for absorption-desorption processes. If we assume, for instance, that we have a distribution coefficient of 0, so this basically means that all the radium is dissolved, so all the radium is in solution, which is not realistic, but works well as an example. And we assume an arbitrary production of 10,000 becquerels cubic meter. So we can see that along groundwater flow path or along specific transit times, notice that the scale is logarithmic. So along this transit time, the activities of the different radium isotopes will continuously increase towards reaching an equilibrium concentration that in this case is equals the production. An important thing is that this rate of enrichment will depend on each specific isotope. It will basically depend on the decay constant specific for each isotope. And for instance, this allows us to see that if we have transit times on the order of few days, basically, groundwaters will become enriched in the short-lived radium isotopes. They will become enriched in radium-223 and in radium-224, but they will not become enriched in the long-lived ones, neither in radium-228 nor in radium-226. But as another important characteristic is that the time needed to reach this equilibrium concentration, it's about 7 times the half-life of each specific isotope. So for instance, 20 days for radium-224 and 1,000 years for radium-226. As I said, so before we were showing this evolution of radium activities by assuming a distribution coefficient of 0, but if instead of doing that, we use distribution coefficients common in saline groundwater and distribution coefficients frequent in fresh groundwater, what we can see is basically that different distribution coefficients influences the radium activities. So the higher the salinity, the lower the distribution coefficient would be, and this would result on having higher activities in groundwater. Interestingly, also, the distribution coefficient also influences the time needed to reach the equilibrium. We saw that if the distribution coefficient is 0, the time needed for radium to reach the equilibrium, it's about 20 days. In the case of having saline groundwaters, this time would be on the order of few hours. And in case we have fresh groundwater, this time to reach the equilibrium concentration would be on the order of few seconds. So I'm showing that only for radium-224, but all the different radium isotopes are showing basically the same patterns. So basically, we have seen that the time needed for radium to become completely enriched depends on the distribution coefficient and also depends on the specific half-life or on the specific decay constant of each radium isotopes. Here, we plot basically the time needed to reach 50% of this equilibrium concentration for each one of the different radium isotopes and as a function of the distribution coefficient. So basically, any value that is above this line will mean that groundwaters are enriched more than 50% in this specific isotope. So basically, we assume that this 50%, if groundwaters are enriched more than 50%, they probably have significant radium concentrations that will allow tracing them if this groundwater discharges to the coastal sea. So for instance, all the waters in here, since they are above all the different lines, so they will be enriched in all the radium isotopes, whilst all these waters here will only be enriched in the short-lived radium ones. So we did this evaluation because it allows us to compare the temporal scales of radium isotopes with the temporal scales of the different pathways. And what we do here is use more or less the common spatiotemporal scales of the different pathways. So we have the long scale processes at the top and the short scale processes at the bottom. And we also classify them according to the different composition of groundwater, basically to different salinities that would basically result in different salinities. By doing so, what we can see is that terrestrial groundwater discharge is likely to become enriched in all the radium isotopes, but on the other side, if we evaluate centimeter scale per water exchange, this process is probably only enriched in the short-lived radium isotopes, radium-223 and radium-224. So, and this is really important, so keep this in mind because we'll come back here later. This is really important because basically it tells us that depending on the pathway that we are evaluating, the enrichments each pathway will have, since each pathway have different transit times, each pathway would have characteristics enrichments in radium isotopes and also characteristic relationships between the different isotopes. So basically different activity ratios. So after this introduction on how radium isotopes are, how groundwaters are enriched in radium isotopes, I will move to the quantification of SGD by using radium isotopes. And the most commonly applied strategy is you constructing radium mass balances, where basically all the potential inputs and outputs are constrained. And then if you assume that the system is in a steady state, you can assume that the imbalance between inputs and outputs can be attributed to submarine groundwater discharge. So common inputs of radium to coastal systems are riverine discharge, sediment diffusion, atmospheric deposition, but this one is not particularly important. And as removal terms, there is mainly mixing with offshore waters that have lower radium activities and also radioactive decay. So by doing this mass balance, we can estimate the flux of radium supplied by SGD by the as the difference between outputs and inputs. And this flux of radium supplied by SGD can be converted to a volumetric water flow of submarine groundwater discharge if we can characterize the concentration of radium activities in groundwaters that are actually inflowing, that are actually discharging into the system. So the famous SGD endmember. To me, or for everybody, I think, this is the most difficult and more important step in any SGD investigation. So how can we determine the SGD endmember? The obvious and easy answer would be, well, it needs to be representative of the groundwater that is actually discharging to your study area. But this is not that simple, and basically it's not that simple because, as we have just said, depending on the pathway, we will have different enrichments in the different radium isotopes. So we can have collecting groundwater samples, we can have activities of radium ranging by orders of magnitude. So basically, the strategy followed to determine the endmember will basically depend on the setting that you are studying. For instance, let's start with a really simple case, a system which is dominated by a single pathway. So for instance, this area here, we have a karstic groundwater discharge. So we can easily assume that terrestrial groundwater discharge is the main source of radium isotopes to our study coastal area, once we have constrained all the inputs and outputs. And if we do that, basically the only thing that we need to do to estimate SGD is basically collecting a sample from the relevant pathway. So in this case would be terrestrial groundwater discharge, so the karstic springs. And if we collect, we can sample these groundwater springs, or if we can sample near shore fresh groundwater wells, we can be more or less sure that we are accurately quantifying, constraining the SGD endmember, and this will give us accurate estimates of submarine groundwater discharge. Importantly, provided that this groundwater is sufficiently enriched in all the radium isotopes, no matter the isotope that we are using, that all of them will produce the same estimates. So, but now we will make the system a little bit more complicated, and let's imagine that we have a system where we have two different pathways, like Alphax Bay, which is a shallow semi-enclosed lagoon located in the Mediterranean. So basically in this lagoon, we know that there are terrestrial groundwater discharge in all this area here through karstic springs, and also there are large fluxes of short-scale recirculation processes occurring all along the system. So just looking at the distribution of the different radium isotopes, 224, 226, and 228, we can already see that this distribution is probably explained by because the different isotopes are having different sources. So here I'm showing basically the concentration, the activity of radium-224, the activity of radium-226 as a function of salinity. Here we have the results that we collected in the bay. Here the results that we collected in port water, in the karstic springs, and also in some streams that are discharging in the area, but they are not particularly relevant as the source of radium. So if we have no idea of the pathways that are discharging in our system, we could do our mass balance, estimate the amount of radium supplied by SGD, and think, okay, we have a lot of springs, so it's likely that the endmember is the karstic spring. If we were using the karstic springs as the terrestrial, as the SGD endmember, depending on the isotope that we were using, we could obtain completely different estimates of submarine groundwater discharge. We could, on the other side, say maybe since it's a shallow area, we have a lot of bioirrigation. Maybe port water it's the main source of radium. So I will use these port waters, these shallow port waters, as the endmember of my model. Then what we could get is also, depending on the isotope used, estimates of submarine groundwater discharge that can vary by an order of magnitude. And with that, what I want to show is that if we have a system with multiple pathways that are isolated, that are not mixing before discharging, depending on, and if we try to use only one radium isotope, this is important, depending on the isotope that we are using, each one is likely to produce completely different estimates. And these estimates will be largely biased towards the pathway that is most sample, that not necessarily represents the pathway that is more important in our system. So the only way to obtain an accurate SGD endmember that would allow us to produce accurate SGD estimates would be weighting the relative contribution of the different pathways. But of course, to do so, we would need some extra information from other methods that is usually not available. So what can we do if we work in a system with multiple pathways? Can we use radium isotopes? And the answer is you cannot use a single radium isotope because, as we have just said, this by using one single isotope, we can obtain completely different estimates depending on the isotope used. But what we can do is combine different radium isotopes at the same time to distinguish and quantify at the same time different pathways. So coming back to the example in an Alphax Bay, we construct a mass balance with evaluating all the outputs, mixing and radioactive decay, and all the potential sources, which are diffusion, inputs from the streams, and treating the two groundwater pathways as two different sources. So basically, we can construct this mass balance, and we realize that we have three unknowns: the flow of water supplied by port water exchange, the flow of water supplied by terrestrial groundwater discharge, and also the water ages or the residence times of our system. So to solve all these unknowns, we need to combine three different radium isotopes and conduct concurrent mass balances for each one of the three different radium isotopes used. And this will produce an estimate of terrestrial groundwater discharge, an estimate of port water exchange, which are completely different than the ones that we would have obtained if we were using only one radium isotope. So this is really nice, but the reality is that we cannot always apply radium isotopes to distinguish and to quantify inputs from different sources, basically because the main requirement to be able to distinguish different sources is that these different pathways, they need to have different activity ratios, so different enrichments on the different isotopes. This is commonly, so if we have two processes, one is short scale, the other one is long scale, most likely, as we have already seen, most likely these two pathways will have completely different activity ratios between different isotopes. But if we have two processes that have more or less the same composition and the temporal scales, we won't be able to distinguish them by using radium isotopes. Obviously, we also need as many isotopes as a known pathway with these characteristics we have. And this might not be always the case. And in these cases, what we need to do is basically combine our estimates with other traces and approaches that can be also plugged in the mass balance. And we can use, for instance, mass balances of radon, of salinity, assessments with temperature, using mass balances of silica, or installation of seepage meters, or some hydrogeological approaches. So, to conclude, basically, we have basically described a little bit the basics on the quantification of submarine groundwater discharge by using radium isotopes. But I particularly like to highlight also at the end why it's really important to identify and distinguish different SGD pathways if we are working with radium isotopes. So first, as we have already seen, by distinguishing different pathways is the only way of obtaining accurate SGD estimates. Otherwise, if we are, I'm talking about systems where of course we have multiple pathways. So if we are not distinguishing them, we are likely to produce estimates that will not be correct, that they can be different depending on the isotope used, and also that will be largely biased towards the component that we have mainly sampled as an endmember that not necessarily represents the groundwater of the concentration of groundwaters actually discharging in the coastal area. Also because if we separate between different components, this will allow us to compare with specific methods that not necessarily integrate groundwater inputs as radium tracers do. For instance, the clear example is there are plenty of models, approaches to estimate the discharge of fresh groundwater to the coastal ocean. But if we provide total estimates of SGD, we cannot compare our radium-based estimates with these studies. So by distinguishing the different processes, this could be also a way of improving the comparability with other methods. And this also links with the next point, basically because the hydrogeological community is mainly interested in understanding or quantifying the amount of fresh groundwater that is discharging into the coastal sea. And if we distinguish this pathway and we can provide some numbers also on these parts, basically we will contribute, so we could use our estimates to contribute a little bit, bridging the gap between the SGD and the hydrogeological communities. And finally, what to me is the most important point. So most of the SGD studies basically try to estimate the flux of nutrients, the flux of carbon, the flux of metals supplied by SGD. And if you want to estimate properly these fluxes, you need to take into account that different processes have different pathways, have different temporal scales. They might have different origins, so they are likely to become significantly enriched in a different manner in the different pathways. And thus, to accurately quantify them, we need to understand the amount of water, so the volume of SGD that each of the pathways is supplying. And I think that's all. So thank you very much for your attention, and I'll be really happy to take any questions, discussions that you might have.
Thanks, Valentí. Great talk, lots of thinking going on there, lots of reflection, so it's lovely to see that. Yeah, so who wants to jump in and throw some comments or questions towards Valentí? Unmute Jan. Jan is jumping.
Yeah, thank you, Valentí, for this nice presentation. I have several questions, but I would like to start with this one. You found these different fluxes based on the various isotopes we are using. The short-lived one, 224, has a different volume compared to the radium-226, if I remember correctly. One of the still very weak assumption we do in all this mass balance is a steady state. And of course, for radium-226, a steady state would mean, yeah, constant system over hundreds of years, whereas short-lived one has a much shorter time scales. So what do you think? What is the error we put in when we assume steady state for such a long-lived isotope?
It's good that you are asking me this question because we are hopefully about to publish, we are still in revision, but with Peter, Joe, Thomas, and many others, we have sent a paper where we try to evaluate the uncertainties linked to radium and radon mass balances, and the assumption of a steady state. It's a big uncertainty that all these approaches have. But this would be particularly, as you say, this would be particularly relevant for the long scale isotopes, not for the short ones, because at the end, all these systems, I'll try to explain from the beginning. So if you have basically the residence time of a tracer in a water body will depend on their main sinks. So we have radioactive decay and we have basically mixing. If our system is governed by radioactive decay, imagine that we have a lagoon with long transit times. So basically radium-224 will decay. The decay of radium-224 will be much more important than the mixing offshore because we have long transit times in our system, which will not be the case of radium-226 and radium-228. But if we have shorter scale systems that are rapidly flashed, for instance, Alphax Bay, which has a residence time of 10 days, more or less, what controls the residence time of the tracer in your system is basically the mixing. So basically the residence time of the water. So you need to validate the assumption during this period. So during this time, in the case of Alphax Bay, we would need to validate this assumption, making sure that all the inputs, all the outputs are relatively constant during the 10 days period. And more or less, I think we can assume that this is the case. So in this case, probably it would not, the uncertainties linked to this, to the assumption of steady state concentrations will not affect that much, I think, the final results. But of course, we have plenty of other uncertainties, so I didn't report the uncertainties, but I would be happy if, I don't think we can report any SGD flags with an uncertainty lower than 50%, because this is what our tracers allow us to do, I think.
So Valentí, we go to Michael Bocher. He has raised his hand, and from Michael to Bill Burnett, okay?
Valentí, very nice presentation. Thank you very much. I really appreciate that you included bitubation as one of the lower scale processes. So would you suggest that we have always to consider, if we do SGD research in the coastal environment, do we have to consider this kind of probably low or small scale fluxes? First question. The second question, what do you think is the lower boundary with respect to the scale? I always have to think about Mandelbrot and when he thought about the length of the coastline of England. And so is it the quartz grain? Is it the lower boundary of fluxes around this grain which are contributing to SGD? Or, but first of all, do we have to consider all these biological impacts in all our systems?
So it always, basically, everything depends on the process that you want to evaluate. The main problem I have, and it's a discussion that we have had in several meetings, if we assume that short scale recirculation processes are not SGD, but long scale recirculation processes are, basically we are introducing an artificial, I would say, arbitrary barrier that basically distinguishes two processes that are almost the same, to my understanding. So what is clear to me is that if you use short-lived radium isotopes to trace SGD, or if you use radon to trace SGD, radon and short-lived radium isotopes will trace everything. So if you have short scale recirculation, it will be traced by radon and it will be traced by radium-224. So providing, if we assume that the short scale recirculation processes are not part of SGD. Basically, it means that when we will conduct our SGD studies, we need to subtract this short scale recirculation processes as if it was another additional source. And this is not commonly done because it requires extra efforts and it's really difficult to do. So my point here is basically, if we are not able to distinguish these two different parts, it's way much better integrating, having a definition of SGD that integrates all the fluxes across the sediment water interface. And then depending on the objective of your study and depending on the characteristics, you can focus on specific components using different approaches or using different methods. And I don't remember the second question. Sorry, Michael.
It was just a question for the lower boundary of considering these small scale processes. So do we have to go even to the fundamental basic structures of detrital material, or is it simply the wormhole or the structure which is given by the macrosolventors?
It depends, because it depends. So we have, as I've said at the beginning, so we have completely different driving forces that can produce this pore water exchange. If we have, for instance, bioturbation, bioirrigation, then it's pretty simple to limit. It's not simple, but you can limit the scale of the lower boundary of these recirculation processes. But for instance, if you have wave pumping or tidal pumping, not in the shoreline, but a little bit offshore, this can also produce large volumes of water coming in and out of the sediments. And this scale would be completely different depending on the driving force of the process. So for me, it depends on the objective you have, it depends on the driving forces you have, and defining a lower boundary is particularly difficult because it would depend on the drivers, I think.
And so we go to Bill in Florida, and then after Bill, we go to Bochao in China.
Hi, Valenti.
Hi, Bill.
Very nice talk. I really enjoyed it. And I really like your pathway diagram. It says things in a very nice, understandable way. So you constructed this very elegant model after showing the case where you have two different pathways, the terrestrial pathway and pore water exchange. I can imagine in many cases, you're going to have more than two pathways. You could easily have three, maybe even all five in some cases. So would the model extend to that many cases, that many pathways? It seems like you're going to run out of, or you're going to have too many variables. What do you think?
Yeah, that's one thing that I haven't said, and I think it's really important. It's that, so if we have pathways that are comparable and they mix before discharge, so at the end you can treat them as if it was a single pathway. So it allows you to rule out some pathways from the equation. What you cannot, what you need to distinguish are those pathways that are supplying different activities of radium isotopes, and with radium would be actually the same case, although it's different because it's way much simpler because it will be enriched everywhere. But basically, so the fact, I don't know what I was saying, but I don't remember what I was saying. Two different pathways. I don't remember. Sorry, Bill, I don't remember what I was saying.
That's fine, Valenti. I get the idea. Yeah, very nice job.
Because I wanted to say something and it just come out from my mind. Sorry. It will come. It will come. Oh. Okay.
So, Bochao, are you still there, Bochao? Do you want to jump in, Bochao? Yes.
Hi, Valenti.
Hi, Bochao.
I have a short question. So when you're thinking about the polar exchange, you're thinking about the biological driving forces. Have you ever thinking about the physical driving forces? Like in some very near shore area with shallow water depth, the mud will be resuspended heavily, especially during the like in China, in the coastal line in winter, the monsoon is very strong. So when the sediment is resuspended, the pore water will be released. But I think it's hard to choose the end member for the pore water in this case. Do you have any comments?
No, the problem to me is that, do we consider this resuspension? So we group it within sediment sources. So and we treat it as if it was diffusion, or we consider it pore water exchange, because there is actually the fact that there is resuspension of sediments is also producing pore water exchange. So I don't know. So I don't know what we say. We have had a couple of sites where we had resuspension, and we basically try to quantify it by doing temporal evolution of the radium activities that we had in this site. And by doing that, knowing the concentration of radium that you have in the particles, you can more or less estimate the contribution that these resuspension events will produce in your system. And this contribution basically includes resuspension of sediments, but also includes this exchange of pore water. So to me, the important thing, more than defining or more than saying, giving a term to that, is explaining so what you are subtracting from the definition. So if you do a mass balance and you can quantify this pore water exchange, and you can subtract it from the contribution of SGD, then it works perfectly. But you need, I think the important thing is assessing and showing what are you tracing. If you are basically quantifying sediment resuspension alone, or if you are also quantifying a little bit of pore water exchange.
So the process I just mentioned is not included in your current model yet?
No, it's not, because it's not an exchange of pore water across the sediment water interface usually. So basically, all these driving forces are based, you can ask Isaac, because he did this nice paper in 2012, I think, where he evaluated all the driving forces of groundwater and pore water. So all the fluxes across the sediment water interface, and sediment resuspension, I think, Isaac, it was not included in this part, because this is like sediment diffusion that we usually assume that it's not a pore water exchange process. But I agree that I think there is pore water exchange, so it could be included within pore water exchange.
Okay, thank you.
So do you have more questions or comments? Anybody wants? I don't have anybody else lining up.
So I can come back to the question of Bill Burnett, because I just basically came out to my mind. So basically what I was saying is that the important thing is that if we have pathways that are mixing before discharge, we can easily treat them as a single pathway. So it allows us to rule several pathways out from the equation. But if we have 5 pathways that are having place in different locations, that are having different radium isotopes, we will always need to provide accurate estimates. We will always need to have 4 radium isotopes, or 4, which doesn't exist because radium-223 and radium-224 basically always have the same activity ratios in most of the sources. So you will need to use some radium isotopes and then try to find other tracers that can help you to distinguish the contribution of the other pathways. So sorry, Bill, but it just came from